Hello everyone, welcome to this lecture. In this lecture I will be teaching you about compressor modeling, right? Compressor modeling, both the single phase, multi-phase compressor modeling, right? So now a compressor is typically an equipment that is used to pressurize a fluid, and in this case is usually a gaseous fluid, right? Gaseous fluid or vapor fluid, right? So you just use it to increase the pressure. So if you want to increase the pressure of a particular gaseous fluid, you make use of a compressor. Now you have different types of compressors, and they are actually grouped based on certain classifications, right? Based on certain classifications. So you have the mode of lubrication, which includes you have oil flooded and then oil free. So oil flooded compressors are compressors that require oil for their lubrication, for the lubrication of their compression chamber, right? While oil free do not require lubrication. Then you have the mode of operation. So for mode of operation, you have positive displacement compressors, and then you have dynamic compressors, right? So now for positive displacement, they work with the reduction in volume of space occupied by the fluid, right? So if you send a fluid into a compressor, the positive displacement compressor would reduce the volume of that gas, thereby increasing the pressure. And this works according to I think the Boyle's law, right? Pressure is inversely proportional to volume. So if you reduce the volume, you automatically increase the pressure, right? So that's how positive displacement compressors work. Then you have dynamic compressors work by increasing the velocity of the fluid, right? So you increase the velocity by probably an impeller, and then that increase in velocity also results into the increase in pressure by that particular compressor, right? So you have the positive displacement, then you have the dynamic. A good example of the dynamic is the centrifugal compressor. Yes, the centrifugal compressor. Then for positive displacement, we have the screw compressors. Then you have the reciprocating compressors as well. So we also have other kinds of classification of compressors. We have based on the number of stages, right? Based on the number of stages, you have single stage and multi-stage compressors, right? So for single stage, the compression takes place in one compression cycle, while for multi-stage, the compression takes place in multiple cycles, right? Multiple compression cycles. Then you also have the mode of action. You have the single acting compressors and the double acting compressors, right? So for single acting, you have the piston. You have the piston moving in one direction, right? Compression takes place in one direction, right? But for the double acting, the compression takes place in both the upward and downward stroke of the piston, right? So for example, reciprocating compressors can actually be designed as either single acting or double acting, right? So let me see. Okay, yes. So based on the mode of operation, this is a chart you can take a look at based on the mode of operation, right? So you have the positive displacement, then you have the dynamic, right? The dynamic. So you have under the positive displacement, you have the reciprocating, and then you have the rotary. Under the reciprocating, you have the single acting, the double acting, then the diaphragm. Then under rotary, you have the lobe, you have the liquid ring, you have the rotary screw, the screw compressor, then you have the vane as well, right? The vane compressor. Then for dynamic, you have the centrifugal and axial, right? So these are the classifications based on the mode of operation, right? This is what you have based on the mode of operation. So that is it, just an introduction to what a compressor is. Okay, so I think we can move over to the simulation environment so that we can start our modeling for today. So we are trying to model compressors. Now I will just use all that is done in this video is just for illustration, right? So just for illustration, I'm making use of these components. Then fluid package is Ben Robinson. Yes, so we are moving into the simulation environment. So your model palette, you have the compressor and then the expander. The expander does the opposite of what the compressor does. So you have the compressor here. So now for compression, you need inlet and outlet streams. Then you need your material stream. So you can easily specify that. Okay. So I've created inlet and outlet streams. So we have this, right? So now for simple compression modeling, you just specify your inlet composition. Now your inlet feed is supposed to be gas, right? Vapor, right? So if you have liquid, it may not solve, but then you can model it as a multi-phase compressor as well. So let's see how it goes. So just illustrations here. So all of this is just assumptions. Now your composition should be pure gas. So I use this. Yes. So now you have all of this. Now you can specify a couple of things for your outlet. So this is just a basic compression modeling. Then we will go into the more complex ones as the video progresses. So now you can specify outlet pressure, or you can go to design and parameters and specify some other things here. You can specify pressure ratio. So let's see if I specify pressure ratio of 5. Let me see. Okay, so it actually solves when you specify pressure ratio. Now pressure ratio is the ratio of outlet to inlet pressure, right? So you have so you have outlet is 506.6, inlet is 101.3. So pressure ratio is 506.6 divided by 101.3. So that's pressure ratio. So I specified the pressure ratio of 5. So what Hysys did was to multiply the inlet pressure by 5, right? So that's how pressure ratio works. So apart from pressure ratio, you can also specify pressure drop, right? So pressure drop also gives you what you are looking for. So if I specify this, if I specify pressure drop, it solves the compressor and it calculates the pressure ratio, the duty, and then the outlet pressure, which in this case is 601.3. So you can also specify other things apart from that. You can specify duty as well, I think. So if you specify duty, it also calculates the outlet pressure and then the other details that are supposed to be calculated, right? So if I remove this, and I can also specify the outlet pressure if I like. So these are some of the things you can specify for your compressor in order for your compressor to solve, right? To solve. So this is like the basics of the compressor modeling, right? You specify your feed composition, then you can specify any of the properties that will actually let your compressor solve. Properties include outlet pressure, then your pressure drop, pressure ratio, or duty, right? You just need to specify any one of them, right? Any one, just one of them, and the compressor should solve. Right now, that's for that. Now, based on what I specified in the introduction, the classifications, we have different operating modes of compressor. So at the moment, you have the centrifugal mode is active, right? And for the centrifugal mode, you have the single, right? The single megawatt, right? So the single megawatt signifies that it is a single stage compressor, right? So you have the single, then you have the multiple megawatt for multiple compression, then you have the multiple IGV. IGV is inlet guide inlet guide vane, right? Inlet guide vane, IGV, right? It helps to control the amount of flow, right? The amount of flow of the gas that enters the compressor or the compression chamber, the IGV, inlet guide vane, right? So you have all these curve options, right, for the centrifugal. So you also have the screw, you have the reciprocating, then you have the wet gas, right? So now, so this is for centrifugal, right? This is for centrifugal. So the next one I want to do is screw, right? So this screw has two options, right? It has the dry screw and then it has the oil injected, right? So for dry means that the compressor, right, is oil free. That's what it means when you say dry. It means the compressor is oil free, so you don't need external oil for lubrication of the compression chamber, right? But if you specify the oil injected or the oil flooded, then you have to create an outlet stream into the compressor that provides that oil for the compressor. So here's what I mean. Now, if you click on oil injected, once you click on oil injected, now you see it says requires an oil feed stream, right? So you are now expected to create another stream for the oil feed, right? So oil will now be fed into the compressor. Now let me explain further. So you are supposed to create a stream for oil. So let's assume this stream is oil. Now you close this. Okay, I think I should just specify it at once. So in this case, I will just make use of water as oil, right? But that is just an assumption, right? So you need to specify properly the components of the oil you are making use of, right? Probably you do that with your hypothetical, right? You could do that with hypothetical. That's if you cannot find the oil in the component list, you can just specify it with your hypothetical. But in this illustration case, I just want to use water, right, for this particular illustration. So let's assume that water is the lubricant. Let's just assume, right? So I just want to send water into this compressor and see how it goes, right? So now that I changed to let's go back there. Now that I changed to screw, right? Screw, you can now find a new stream, right? A new stream for the oil feed. So you can attach a stream there, right? You see, so once you attach that stream, the whole thing solves again, right? So you have the feed, then you have the oil for lubrication, and then you have your output, right? Your output. So you still specified outlet pressure, and then everything solves, right? So this right here is for the screw compressor, right? The screw compressor that requires oil for lubrication, right? So like I said, if you cannot find the oil you are looking for in the component list, you probably need to specify it as a hypothetical component and then use it as your oil feed, right? So that's for the oil flooded compressor modeling, right? So that's for that. Then what can we do next? Let me see. Okay, so we still have, I think reciprocating is easily understood because it doesn't have any section. Then we have wet gas. Yes, so we have wet gas. Now for wet gas is used when you have liquid, a certain amount of liquid in your gas feed, right? So for example, this gas feed we have is purely gas, which is methane. But imagine there was a little amount of liquid in it, you will see that this compressor will no longer solve. So if you change the composition, you have let's say you have 0.5 here, 0.5, yes, then you also have 0.5 here as well, right? Okay, wait, let me see. Okay, let me detach this. Let me detach this first. Detach this, and I want to change it back to delete. I want to change this back to the centrifugal. Okay, now then I now go back to my feed and change the composition. So I'm going to add some water to this. So we have 0.8, let's say 0.8 methane, and then 0.2 water. So now you see the compressor no longer solves, right? So the compressor no longer solves, and it is because there is a liquid in the inlet stream, right? Because I added some water to the inlet stream, so the compressor no longer solves, right? So now to make it solve, you have to model it as a multi-phase compressor, and you can do that by clicking on wet gas, right? So once you click on wet gas, it solves, right? It solves back again, right? So you have the compressor converging again, and you have the OK message, right? When you use the wet gas. And for wet gas, you have both the single curve input and the multiple curve input. GMF, GVF stands for gas mass fraction and gas vapor fraction. Yes, right? Gas mass fraction, gas vapor fraction. So you can have curve input for both the single and the multiple, right? So this is for multi-phase modeling of a compressor. You make use of the wet gas option, right, in order to solve with a stream that has liquid or certain amount of liquid in it, right? So another very important thing you have to consider in modeling of compressor is efficiency, right? You have the adiabatic efficiency and then the polytropic efficiency, right? So the efficiency is also another very important thing you have to consider when modeling compressors. So you have the adiabatic efficiency as the ratio of work input required by the adiabatic compressor to the work input required by a real compressor. And you have to note that the adiabatic efficiency does not take account of heat transfer into the system and out of the system, right? So it doesn't take account of heat transfer. Then you also have the polytropic efficiency, which is the ratio of actual work done to the theoretical maximum work that could be done, right, by that particular equipment. And for polytropic efficiency, heat transfer is accounted for, right? So technically, I think polytropic efficiency is usually higher than the adiabatic efficiency, right? And when you are modeling your compressors, you have to specify one of them, right? Either you specify the adiabatic or you specify the polytropic, right? Whichever you specify, Hysys will calculate the other one. For example, here automatically adiabatic was specified, right? Then Hysys calculated polytropic. You can actually change your efficiency. For example, if you change the adiabatic efficiency to 85, yes, 85. So Hysys calculates polytropic as 86.997. Then if you specify polytropic as, let's say, 85, you see Hysys calculates adiabatic, which is less than polytropic, and then the value is 82.695, right? So one of these efficiency values, right? One of these efficiency values must be specified, right? So that's how it works for efficiency, right? And you know that the efficiencies, right, affect the duty or the power requirement of the compressor, yes, right? So the efficiency has an effect on the power requirement. So if I reduce it to 80, for example, you see that the power requirement has changed, and at 85, yes, at efficiency of 85, the power requirement has reduced. At a polytropic efficiency of 85, the power requirement has reduced, right? So that's it for efficiency. You have to specify one of them, right? You can't specify two of them at the same time. If not, your system will be over specified. So you either specify the adiabatic efficiency, or you specify the polytropic efficiency, right? So the next thing we will be treating is curves, right? Adding of curves to your compressor. So for that, we'll be making use of this data here, right? So we are making use of this. We are making use of this for the addition of curves to compressor. So for that, we are going to be using our model, right? So this is what we have been modeling for a while. So this is where we'll be adding that particular compressor to. Then when we add it, we'll now specify the curves inside the compressor, right? So if you have been following the simulation series, you would be at this point. The last tutorial we had in the simulation series was the rigorous exchanger modeling, which is this right here. So now for this two-phase separator, we are adding a compressor to the vapor outlet or the gas outlet, right? So we'll be adding a compressor here, then we'll be adding the curve to it, right? So that's it. So quickly, so you just get out a compressor. Okay, so this is a compressor, and attach it here. Let me see, I'll reduce this a little. Okay, yes, so we can now let me see if I name this. Okay, so we have that, and we have our energy stream. Then I think it should be this, right? So once you are done specifying this, you can specify your outlet pressure. Outlet pressure is 600 kPa. 600 kPa. So once you specify it, the whole thing is solved. So the next thing is to now specify the curves, right? So we are specifying curves. Now for curves, we are going to be doing that in the rating section, and our efficiency for these curves is adiabatic. For this particular illustration is adiabatic. So if you want to specify curves, all you need to do is to click on add curve, right? So once you click on add curve, it gives you the opportunity to actually specify those details of that particular curve, right? So now for this so in this window, you can specify the curve details, right, from your data. So for example, we'll be specifying all of this in that first curve, right? So we'll be specifying all of that. Then before we do that, we can take note of the efficiency, the adiabatic efficiency. So the adiabatic efficiency is 75. Yes, it's 75 at the moment, right? So it's 75. Now after we have specified the curve for this particular compressor, it's going to have an effect on the adiabatic efficiency, and we'll be checking that after we do the specification, right? So for now, the adiabatic efficiency is 75. So based on the curve we specify, Hysys will calculate a new adiabatic efficiency for this compressor, right? So let's get into specifying this curve. So from our data, we have the speed. The speed is 5,000. Yes, 5,000. Let me see. Yes, 5,000 RPM. Then we have the flow. We have the volume flow, and the unit is this. So that's correct. Then we have the head in meter. Head unit is in meter. So we can just enter the values. And then we have the efficiency for each flow. Yes, so we can just start entering the values quickly. Volume flow 3,100, 3,172. So you just keep entering the values until you are done, right? So we are done with this first curve. So you just enter the values you have, then you can do this. So this is for this one. Then we can add another curve. For the second data, we have RPM of 7,000. Then we have all of these values. So I'll just be entering all of that now. So we have curve 2. So RPM 7,000. Then we can start off specifying all the values. So the first one is 1050 for volume flow, 1050. Then you have head as 4600, then 72%. So just enter your values and then 72, enter. So I will specify all the values. So we are done entering the values of the second curve as well, right? So after doing that, we can now activate curves. So you just click on activate, and then you activate the second as well, right? So after activating your curves, you can click enable curve, right? Enable curve. So once you click enable curve, it calculates compressor speed, right? It calculates compressor speed and then also efficiency, right? So you can go back to, for example, you can go back to ratings. You see that the efficiency, adiabatic efficiency has reduced, right, from 75 to this value. So you see that it has reduced even the polytropic efficiency, and then Hysys had to calculate both of them in this case, right, because of the curve data that was specified in this rating tab, right? So you activate the curves and then you enable curves, right? So it then calculates the compressor speed as well. So you can check performance, right? You can check performance of the compressor based on the curves you have specified, right? You can also view the curve plots if you want, right? So this is the performance. You have the power, then the efficiencies, then the speed as well. The speed is now calculated. So you can also view the curve plots, right, by clicking on plot curves. So it gives you the plot. So you can view plots of both curves, curve 1 and curve 2. I think curve 1 is the red plot, right? While curve 2 is the green. So if you want to view it in a larger frame, you can actually view it like this. So this is your plot based on the data you have specified, right? So this is how to add curves to your compressor in Aspen Hysys, right? This is how to add curves, right? So I think we'll be stopping here for this particular tutorial. If you have questions, you can let me know in the comment section. You can let me know in the comment section. Then like this video, follow, subscribe to this channel. Subscribe to this channel if you have not done so yet, right? Then share this video with your friends. Thank you for joining me in this particular tutorial. Thank you. Do have a nice day.